5 of the prestigious iCon BCI lecture series. Just as the previous session brought together brilliant minds to exchange ideas and insights, today promises to be yet another enlightening experience. We are honored to have with us Dr. Midhur Kumar Ahirwal, our esteemed chief guest, whose expertise and contributions are invaluable. A warm welcome as well as to all the scientists, respected faculty members, and participants who have gathered here today to continue this journey of learning and collaboration. Now, it's my pleasure to invite our speaker, Dr. Midhur Kumar Ahirwal. Dr. Midhur Kumar Ahirwal is currently working as Associate Professor in the Department of Computer Science and Engineering, Maulana Azad National Institute of Technology, Bhopal. He also worked with NIT Raipur and NIT Delhi. He has completed his PhD from IITDM, Jabalpur in 2014. He has more than 10 years of experience in teaching and research. His area of specialization includes brain-computer interface, artificial intelligence, soft computing, evolutionary intelligence, biomedical signal, and image processing. He has published more than 70 research papers in Scopus, indexed journals, and international conferences. He is a senior member of IEEE, International Association of Engineers, Indian Academy of Neuroscience, and Soft Computing Research Society professional bodies. He has successfully implemented brain connectivity network analysis and advanced filtering methods to enhance the signal to noise ratio biomedical signals. His expertise is demonstrated through high impact publications in indexed journals, showcasing novels approaches in mental health monitoring, adaptive noise cancellation, and functional network analysis. This interdisciplinary approach combines AI and biomedical engineering, ensuring the successful implementation of AI-driven healthcare solutions. Over to you, sir.
Okay, thank you very much for nice introduction. Now, first of all, I would like to thank CDEC for inviting me for this lecture series on brain-computer interfacing. So basically, I have created this presentation to explore some fundamental of brain-computer interface and what are the traditional machine learning things that we are using in the early days, and now what are the advantages, or you can say things we are getting from the deep learning. So I will discuss one small deep learning model also, and if time permits we can also see some tutorials and hands-on that how whatever data is available on the different websites nowadays we can process that also. Okay, so first just take a glance or look over that how this brain computer interface or BCI things means what is the core concept of this technology. So in this, basically, if you are able to see this diagram, in this first part is the signal acquisition part. So you can see one human brain is there, over which we will put some acquisition system and collect the data in the form of EEG signal that are called as the electroencephalogram signal, or generally known as the brain waves also. And then the role of signal processing comes. So in early days, we need to do lots of pre-processing over the signal, then we need to extract the feature, and then we need to apply the classification methods. So in these three, we can say this is the part of system. Major part is the pre-processing and the analysis. Then feature extraction, we have basically three domains. Either we can extract the feature in the time domain, or in frequency domain, or time frequency domain, both. And after that we can apply any simple classification technique and we will get the output. So basically these output are translated into different type of commands, and these commands are basically used to operate or drive any kind of device, or we can also use these to control some software command. So this is the general concept of the brain computer interface. Means without any physical movement, if we are able to operate the computer or any physical device, so that is called the brain computer interface. Means just the power of our thoughts we are using to control the outer world things. Now in this slide you can see in which cases we can use the brain computer interface. So basically if you look this first diagram, so generally what happens whenever we need to move our any of the body part, so basically the things started from the brain only. Means our brain will give the command that what body part we need to operate. So from the brain different type of signals will pass through our nervous system, and that will evoke the potentials. So with the help of nervous system we are able to operate the hand and leg and different kind of movement. So if due to you can say some accident or injury, if we are not able to operate any body part with the normal pathway, so what happens, this normal pathway is breaking down and we are not able to operate our body part. So we are taking the help of the brain computer interface in which we are recording these thoughts, or we can say brain waves, or technically we can say we are recording the EEG signal, and then we can apply the concept of brain computer interface and we can operate any you can say robotic or the mechanical arm to do a specific kind of work. So in the last, you can see after the translation into the command, we can directly operate any wheelchair, or we are able to write the text. Means if some person is not able to express the emotion or not able to talk, so he can directly write the text with brain waves only, or we can use those command to for the electric switches also to operate the electricity. Then we can also use for the entertainment purpose. Means nowadays many gaming systems are also available which are operated with the help of BCI systems. Now here are some example. So in this picture you can look, one person is there that is wearing the EEG cap. Means different electrodes are there by which we are collecting the electroencephalogram signal. So this first is the application in which one person is sitting and he is able to navigate inside the virtual world with the help of EEG signal or with the help of concept of BCI. Second is the same application of one robotic arm is there. So we can also operate that robotic arm with the help of our EEG wave or with the concept of BCI. Then this third one is a picture in which two persons are sitting and both are using their EEG or the brain power to play a game. So basically this game is in such a way that one ball is there and both players are trying to put that ball into the opposite goal. Then this assistive robotic arm is there. If due to some mishappening we are not able to operate our finger properly, so this mechanical you can say support will assist our movement, and it is also basically operated by the EEG signals only. So it will provide some more strength to our finger, so we are able to perform the desired operation. Okay, then this last one is a very you can say famous application of EEG. It is called the P300 speller application, in which like the 6x6 or 7x6 7x7 matrix is there, in which the English or the Hindi alphabets are arranged, and one by one they are blinking row wise and column wise. So after the entire you can say phase is over, so one by one we are able to spell out the characters. So at the end we are able to write the complete word or the complete sentence, and it is basically used by the patients that are suffering from the paralysis, who are not able to operate their move their body part, or not able to express, or not able to communicate anything, but their brain is working fine, so they can use this BCI, and they are able to write the word and the entire sentence. Now here it is a very you can say brief introduction about the EEG signals. So basically EEG signal is having the frequency spectrum started from 0.1 hertz to say up to 30 or 35 hertz. And these are the five basic categories of EEG signal. First one are the delta waves, the EEG wave which are having the frequency less than 4 hertz. And these type of signal or these types of frequency are basically generated when person is in deep sleep. And in parallel, you can also look that diagram in which the first plot is corresponding to the original EEG signal, means raw EEG signal that we are collected. So it is more or less looking like a random signal. So that's why it is, you can say, one more limitation or disadvantage of EEG signal, that just by looking over the EEG signal plot, we are not able to interpret anything, that what is going inside that signal or what type of task is performed by the subject during the recording of the signal. And if you are able to compare that, if you will recall the waveform of ECG, electro cardiogram signal, the signal of the heart, so in that we can easily able to identify the peaks. So by that we can easily calculate the heartbeat, but it is not uh, happen in the case of EEG, because it is also you can say having the so much of frequencies and random type of signal is there. And if you will look the delta wave, so you can see it is the slowly moving wave, means most of the brain part is in the resting state. So that's why this very slow wave is there. Now second one is the theta wave, which is having the frequency band from 4 to 8 hertz, and it is the wave which is generated corresponding to the meditation state, when person is sitting relaxed and practicing the meditation. So you can say, as compared to the delta wave, theta wave is little bit higher in the frequency and more frequent changes are there. Then comes the alpha wave. The frequency band is 8 to 13 hertz and it is corresponding to the relaxed state. Means person is fully awake, but it is not performing any, you can say, physical activity. Then comes the beta wave. So this is active or working state, and the frequency band is between the 13 to 30 hertz. And this is, you can say, most commonly frequency band that is used in the creation of BCI systems. Why? Because we need to identify the pattern or the conditions in the EEG signal when person is in the active or working state, performing different kinds of mental or physical activity. So in this, you can see the beta wave. So again, you can say so much changes are there. And last one are the gamma wave. And this particular band is rarely used for the analysis because it is related to some hyperactivity going inside the brain or higher level of meditation, means your signal is having the very high frequencies. Now we can move to the second part, that is the traditional machine learning or the classification systems. So we all know about the machine learning practices. Just we can first look over what is this traditional AI techniques. So in very early stage also, when we are having the data logic and we are simply applying the logics over the data and we are getting the output. So this, in the beginning, AI is only limited to certain kind of fixed rules, means we need to simply apply the rule over the data. We can consider a simple case of threshold, say like if any signal or any value is coming below or above that particular threshold, so we need to make certain kind of decision. Then machine learning comes into the picture, in which the thing is that we are having the data and we are having the output, and by combining them we are interested in finding out the logic, means the relation between data and the output. So this is the, you can say, basic concept of the machine learning. So in this also, these techniques are basically the data driven, and if we are changing the data, so your logic will also change, because it is just the pairing between the data and the output. So now see, your machine learning workflow basically start from the data, because it is totally the, you can say, data driven thing. So whatever data is there, that data we need to use for the training purpose. And once we are done with the training, so we can say our machine learning model is trained. Now we need to take the help of test data to basically test the performance of that particular model. And why we require this test data separately? Because during the training, your model is already seen the different kinds of pattern that are available in the database. So what happens if you are testing the model with previous testing data? So it will always give the good accuracy. Why? Because it has the model has already seen the patterns or seen the conditions, or you can say patterns inside the data. It is the, you can correlate with the same cases. If I am giving the some solution or the problems during the normal lecture, and same problem and same question if I ask in the test or exam also, so students will easily solve that problem. Why? Because they have already done the practice over those questions. So that's why we are giving the different question in the exam, just to check their learning. So for same, we need to arrange some test data, or we can use any new database also for the testing of model. Then we can apply those test sample on the model, and after that we will check the answer. So this is the, you can say, basic flow of the machine learning. Means we need to use the training data and separate testing data to test the model, and for training purpose we can use the training data. And in general, what happens, whatever database is given to you, so first basically we can split that data into two parts. Means say if 100 samples are there in your database, so generally we are keeping the 30 samples apart from that database, and 70 percent, or you can say 70 samples we are giving as the training, and rest of that 30 sample we can use as the test data. So in when we are coming to the deep learning things or the deep learning models, so how it is different from the traditional machine learning practice. So when we are going to develop any machine learning model, so one thing extra is required, that is the feature engineering or feature extraction part. So in that, either we need to go for the time domain feature extraction or the frequency domain feature extraction in case of the EEG signal, or in case of the concept of BCI. So again, one question comes, how many number of features are good, or which features are good? So again, you can say confusion, or lots of exercise we need to do with the pair and combination of features, and then we can apply any of the machine learning techniques. So machine learning technique, basically we can see the support vector machine, or your decision tree, okay, or simple artificial neural network, all comes under the traditional machine learning. For those, we require the feature extraction also, or we can say the dimensionality reduction techniques also. While what happens in the case of deep learning, we can directly put the raw data into the model. No feature extraction or no feature selection is there. So whatever raw data is with us, if we are interested in applying the pre-processing, so we can apply some filter or any pre-processing kind of thing. And after that, we can give the filtered data to the model. So model itself extract the feature. So basically in any deep learning model, two parts are there. First part we can say as the feature extraction, means automatic feature extraction is there. And then those features will be transferred to the classification part. And they say that is more or less, you can say, traditional artificial neural network only. And then we will get the classification results. So here we will discuss a simple case of convolutional neural network, because these are the, you can say, most famous type of deep learning methods. So in this, convolutional neural network basically works on the principle of the simple convolution operation that is very famous in the image processing or the computer vision field. One small kernel is there that we need to mask over the entire image, and we will get the feature, or we can say we will get the one new image. So this type of network or this convolution neural network is basically designed for the computer vision purpose, but nowadays it is used in you can see all the type of data, 1D, 2D, 3D, means signal, image, or videos also. And basically, whenever we are designing any convolutional neural network from the perspective of the deep learning model, so different type of, you can say, hidden layers are there, and each hidden layer consists of one convolution layer, one pooling layer, and one fully connected layer. So these are, you can say, the basic components of any deep learning or CNN model. So here is just a small, you can say, workflow of CNN model. So here you can see this input is there that we can consider as the you can consider as the 2D image, or 1D signal. We can also arrange in the same way. Now we will do exercise over one database also, a small exercise. So basically this input is there that you can consider as the image, and that small block, this is basically the, you can say, just this small block. Okay, this portion of signal or image we are taking, and this small box is considered as the kernel. Okay, in which few weights are there that will be updated in each and every iteration. So by applying the convolution operation between this entire image and this small block of weight, we will get these feature maps. So from one filter or from one kernel, we will get this one feature map. So if we are increasing the number of filters, so we will get the different feature maps. And after that, this pooling stage is there. So basically this pooling stage is nothing but simply a drop down, or you can say the subsampled image. Means by using any concept, we are simply discarding few of the data points of few of the, you can say, pixels in this particular image. So your that feature map will be shrink to a small size. And after that, again we need to apply the second convolution layer. Means again one kernel we need to take, and again we need to process those features, or you can say new images, new small images, through that CNN layer. And again we can apply the pooling layer. In between also small layers are there that we will further discuss when we will see the model. And after that, once you are done with this convolution pooling pair, then we need to use this fully connected layer, in which we are converting all these 2D metrics into a single 1D array. And then we need to apply the concept of artificial neural network only. And at the end, we will get the output. So this is, you can say, a very basic or the general architecture of the convolution neural network. So here is just one example. So you can see these are the image metrics or the pixel values, and basically this small portion. Okay, this is the 3x3 kernel or the filter that we are using. Okay, so in this you can see some zeros, -1, 5, some values are there. So for a specific kind of you can say feature extraction, we need to use the specific weight. But when we are talking about the convolutional neural network, so at that time these weights will automatically get updated. We need not to decide that. So these weights will be convoluted with this image part, same number of pixels, and we will get this single value. So in that way, this kernel will rotate over the entire pixels, and we will get this feature matrix. Means you can say the processed image. And after that, in case of max pooling, say if we are choosing the size 2x2, so in pair of 2x2, one value we need to discard. So 2x2 means 4 values will be there. And if max pooling we are using, means only the maximum value we need to keep, and rest of the values we need to discard. So in this portion, you can see 20 is remaining. Here 30 is remaining. In second, this 112 is remaining, and last one, this 37 is remaining. So you will get furthermore small matrix. So this is basically the your feature extraction part. Means how we are reducing the dimension with the help of CNN layer. So now this is one CNN model that we have created, and we have also tested this on several databases, and it is performing a well over variety of databases. So this I will try to explain you in a simpler way. So here, if you will look the dimension of the input, in this I will fit one EEG database. So here you can see this is the matrix of 19,200 cross 14. So this 19,200 are basically the time instances. Okay, and this 14 is basically representing the number of EEG channels or number of EEG electrodes. So this matrix is something looking like this. Okay, so on basically x-axis, you are having the time instances, and on y-axis, you are having the number of channels. So 14 channels are there of EEG, and 19,200 are the data points or the discrete samples of EEG will be there. Okay, and this basically we can simply calculate from what is the sampling frequency of EEG signal and what is the recording time. With the help of these two things, we can easily calculate this number 19,200. So basically, previous slide we have just discussed the 2D convolution neural network, and here we are using the one-dimensional convolution neural network. Means your kernel is moving in one direction only. In case of image, we need to move that in both the direction x and y axis, but here we need to move that kernel only into the one direction. So that's why we are saying it is the 1D convolution neural network. So that kernel we need to move along the axis of time. So it will cover the entire signal. Okay, so that's why you can see these small blue arrows are there that is showing the direction of movement of kernel. Okay. And here you can see kernel size, we have taken the 4. In previous case, say 3 cross 3 or 4 cross 4 is there. Why? Because we need to take the square matrix here. Just 4 kernel weights we are taking. So that's why the kernel size is 4. Means 1 cross 4 we can consider. And number of filters are 128. Means 128 times we need to apply that kernel. So we will get 128 feature maps. And then one max pooling layer is there. So same operation will be there. Means subsampling we need to perform. Then one batch normalization layer is there. So basically work of batch normalization is simple, that it will normalize the whatever data matrix we are getting in this, feature matrix we are getting in this, it will normalize the values inside that. Then one dropout layer is there. So basically the role of dropout is that randomly it will off the updation of few of the connections. So it is basically used to avoid the overfitting into the network. Then same structure we are repeating with kernel size 8 and the number of filters 64. Then kernel size 16, number of filter 32, means simply 3 convolutional layers we are repeating with different parameters. And at the end, we need to use one flatten layer. So all the feature matrix we are arranging into the 1D array, and then we need to apply this dense layer. Dense layer is very simple. It is simply working on the concept of artificial neural network, means fully connected network. And at the end, we are having one output layer. So this output layer we can adjust based on the number of output classes. So binary classes or 3 class or 4 class classification we can easily perform with this model. Okay, after this is the you can say the same thing, all the parameters in this particular you can say in the form of the a table, same kernel size. This their ReLU function is used. ReLU is basically the activation function that is applied after the convolution layer. Pool size is 2. Okay, here the same parameters are there. Okay, and this is the 100 units inside the dense layer is there. Okay, here one you may get confused with this number. Okay, so this we will just correct why it is 798, because it may happen that we have segmented the signal. Means here we are saying that 19,200 samples are there, but here we have written 790. So it may be the case that we are performing segmentation over the signal. and only this part we are giving at a time. Okay. Now see, this we have applied on one mental workload database that is freely available on the IEEE and many of the website also. So here you can see nowadays this mental workload or the cognitive workload BCI is we are famous in different application. So this is you can say a key parameter to access that if person is performing any you can say specific type of job where the you can say assessment of its mental health is required, and say if it is performing some say driving operation, okay, and after some time it is feeling the drowsy or because of any reason its attention is not over the driving, means the person is distracted. So at that time if our system is detecting that person is not fully you can say performing the attention or giving the attention over the driving only, so we can generate the alert. So basically this mental workload is nowadays you can say a new research area, because in most of the time if you will look for the literature review, you know, either the motor imaginary BCI means the physical hand or leg movement and the imaginary hand and leg movement things are resolved by the help of BCI, or your EEG signal are used for the clinical purpose only. Okay, so this is the you can say one recent field over which you can focus for the further research. So in this type of study, we applied our model, and database that we have taken is this STUW database, that is simultaneous task EEG workload data set. In this person is performing multiple activity at the same time, and we are able to tell that what amount of mental workload or cognitive workload is uh, over that person. And as we all know that we are having the limited EEG databases, means very fewer samples are there. And the requirement of deep learning is that it requires the lots of data for the training. If you are giving only few samples, so it will not give the good accuracy. Though your traditional machine learning techniques, because of handcrafted feature, they are giving the good accuracy, but it is not true in the case of deep learning. You need to give the lots of data, then only it will give the good accuracy. So that's why we generally use this smooth technique, that is the synthetic minority oversampling technique. So by this we are able to increase the number of EEG recording or number of EEG samples. So say in your database, if you are having the 50 subjects data only, and you can apply the smooth technique. So by that you can increase as much as samples are required. Okay, means synthetic data you are creating. Synthetic EEG data we are creating with the help of this smooth technique. Okay, and after that we can achieve a good classification accuracy. So it is just a little description of the EEG data set that we have used. So here you can see the 48 subjects or the participants are there in that multitasking workload experiment that is using this particular SimCap multitasking test. So again, it is the well-designed software in which we can one by one increase the task. So multiple tasks are there, like recalling task, calculation task are there. They are flashing some numbers on the screen, and we supposed to count those number, perform some arithmetic calculation, mental arithmetic we need to perform. We need not to perform on the notebook. Mentally, we need to recall all the things. In parallel, they are also adding some recall technique, means they will flash the name of some person, and we need to recall their mobile number or landline number also. So in that way, multiple mental tasks they are giving on the same screen, and at the end they are taking our feedback that after performing these activity, what is the mental workload you are feeling. So we need to rate on the scale to 1 to 9. So after that, they will compile the entire experiment and suggest that, okay, this person is rated to 9 or this person is rated to 1 or 5. So based on that, we can generate the classification levels. And after that, we can put the class low, medium, high mental workload. Okay. And these are the signal parameters, like say this emotive EPO, epoch is the name of the device by which the EEG signals are recorded. 40 channels recording is there, and 128 hertz sampling frequency is there, and the recording time is 2.5 minutes. Okay, so if you can calculate 128 into 2.5 minutes, we need to convert into seconds, so you will get that 19,200 only. Okay, so now we can for the remaining time, just we can go on to the one tutorial of the same database. Okay, so see, this tutorial I have created on the Kaggle, in which you need not to import the database, because we also uploaded this same database mat files in this Kaggle notebook. Okay, so it automatically linking with that particular database. Just we will put the means print the shape that we are getting from these metrics. Okay, so here you can see these output. Okay, so basically these are the metrics that we are using. One data set matrix is there, one rating matrix is there, and one this class labels is there. Okay, so in the data set, we are having the EEG signal. In the rating, we are having the rating given by those participants. And in the class, we are having the class label. So basically 0, 1, and 2 are used to define the low, medium, and high mental workload. Okay, so this shape you can see 14 cross 19,200 cross 45. Why it is 45? Say in slide we have seen 48 subjects are there, but few of the subjects are not given the proper rating. So that's why the data is discarded. So actually we are using the 45 subjects data. Okay, 14 is the number of channel, and this 19,200 is the time sample that we are getting after the multiplication 2.5 into that 128 hertz sampling frequency. Okay, so can anyone confirm that you are getting the same thing? And let me also once cross check. 2.5 into 60, so say 150 seconds are there, and into 128. Okay, so total 150 seconds data is there, and if we will multiply 128 hertz sampling frequency, so exactly you are getting the 19,200. Okay, and this 45 cross 1, 45 cross 1 is nothing but the same rating and same this class labels size is there. So all metrics are well configured, means 45, 45, 45 means 45 subject data is there and 45 labels are there. Okay, then this small code of reshape is there to align all the things. So here 45 and 45 are perfectly aligned. So basically one is the data matrix. This first one is the data matrix and second is the your label matrix. And now see, this is the small code for train test split of the data. So here we are putting that data set matrix. We are putting these labels. Okay. And after that, we are defining the test size. So the 0.10 is basically defining the 10% of data we are removing from the entire matrix. Okay, so after running this, see, first we are printing this X train. So this is the train database in which we are having the 40% data, other dimension are same. And then next is the X test. This is the your 5 samples only that we are keeping for the testing purpose only, and other dimension are same, and same happens with the your class label also. So 40 gets separated and this 5 gets separated. So this 5 and 5 we are using for the testing, and this 40 and 40 we are using for the training. Okay. And this line is just to check the wide test. So in testing, you can see 2 samples are there, whose output is 1 1. One sample is with 0 output, another 2 with 2 2. Means all 3 class data is there in the testing phase, in the testing database. And now see, this is few lines of code for building that CNN model. So it is also very simple. We are using this Keras library, in that we are building that sequential model. So sequential, basically the data and the matrix is moving sequentially one by one. And here you can see this is the convolution 1D layer we are adding into that particular model. So here model dot add is there. Okay, I am little bit moving fast due to time constraint. Okay, so here you can see 1D matrix is there, and see same parameter we have designed. Number of filters 128, kernel size 4, activation function relu, and input size. So you can see from that slides you can easily correlate 19,200 comma 14. So 14 number of channel and 19,200 is the signal length or the number of data points in one channel. Okay, after this max pooling layer is there. Max pool size we are defining 2. Okay, then this batch normalization layer. Okay, then dropout is there, that we are defining this 50% means 0.5. Then again we are using the second convolution layer. So here filter size is 64, number of filter is 64, kernel size is 8, and then this review activation function, then pool size 2, then again one normalization layer, then third layer, this is dropout, and then this is the third layer in which kernel size is 32, sorry, filter number of filter 32, kernel size 16, and again review function. And same batch normalization, max pooling, dropout is there, and this is the flatten layer. Okay, so flatten layer is simple. Whatever previous feature matrix is there, all we need to arrange in the one-dimensional array. And after that, we are using this dense layer with 100, you can say, neurons. Activation function is relu. And one more dense layer, this is acting basically as the output layer. So that's why one neuron is there to produce one output. Okay, and it is having the softmax function. Okay, and at the last, this compile. In this, we need to define which type of loss function we need to use, what type of optimizer is used to train the entire network, and what type of metrics we need to use the this entire scenario. And all these parameters we can change. I will also give you one link in that you can see the varieties of you can say parameters are there. Okay, and this is the you can say training part. With the help of this model.fit command, you can train the entire model by giving the x train means training data, y train means training labels. Okay, we can tune this batch size and number of epoch. So this I am keeping the minimal so that model will run within just a minute. Okay, let me compile this model first. Okay, so this red color is not the error, it is just some warnings. So now this C model training get started. So you can notice we are having just 40 sample data. So that's why very less accuracy is there. Only 39 or 38% accuracy we are getting. Or sometimes we are getting 42% also. And this is just why because only 40 samples are there. Okay, then training is over, though we are getting the less accuracy, but model is successfully executed with that small data also. Okay, now this model that evaluate command is there, in which we need to pass see this X test, means test data sample that we are saving. Okay, and this Y test. So see, in this testing phase also we are getting the 40% accuracy only. Okay, this code, small code, is just for the creation of you can say confusion matrix that mostly we are reporting into the papers. Okay, so here you can see this is the confusion matrix. So in this you can see all the samples are basically classified into first class. Okay, you can see this 1, 2, 2, and all the samples, 5 samples are there in the testing phase, and all the samples are classified into one class only. Okay, so this confusion matrix we can use for the further analysis, like which class is highly having the misclassified number of samples. So by doing these repetitive exercise, we can tune the uh, accuracy of each class also. Okay, further is the detailed of you can say sensitivity, precision, recall, etc. But I think now you get clear idea that with this small amount of code we can implement any deep learning model. Only this part we need to tune. Not tune means this part we need to redefine. So say if you are finding any architecture in the literature, different deep learning models are there. So simply those layers you need to add in this, and from where you will get these layers. Okay, so this entire Keras website is there. In that you can see different models are there. Okay, and see different layers are there. Okay, like in case of convolution layer, pooling layer, recurrent layers are there, pre-processing layers are there, normalization layers are there. So all the layers are available here. Okay, so like in case of convolutional, and if we are going for this say 1D layer, so here you can simply read out what are the specification, what are the things we can use the value for different parameters, and easily you can define or build your own network by making small changes. So here you can see this is the small line of code is given in which you can see as the exercise, like 32 filters are there, 3 cross 3 matrix they are using, activation function, and this is the X input. So you can simply read out from this website. Okay, again you can see different optimizers are there. SGD is basically for your stochastic gradient descent method. Okay, in that you can define the learning rate, momentum, different parameters you can tune. Okay, apart from this, RMS algorithm is there, Adams algorithm is there. So different varieties of algorithms is there. Okay, in the same way, different metrics are there, like accuracy class, binary accuracy. So all these you can simply use in your code for checking their effect in your deep learning system. So now I think only 5 minutes are remaining. So this 5 minutes I'm just keeping for question and answers. So if any participant have any type of doubt or want to discuss anything, then please ask.
Participants can unmute one and ask the question. At a time, one participant can ask questions.
Sir, I have a small doubt, sir.
Yes.
Sir, what exactly means this epoch is equal to 5, sir? It means how many times the model wants to get trained, sir? Or it's
Yes. Yeah. Okay. See, this epoch basically means how many times we need to iterate over the entire database. Okay. So say if we are keeping this 1. Okay. And if I will again run that, Okay, let me make one more change. See, epoch is basically this one by one means the entire database I need to give as the training for just one time. Okay, and if I am updating it to 2 means the entire database is processed 2 times for the training purpose. So this is the epoch 1, accuracy is 40%, and now it is for the epoch 2, again accuracy is 40%. And if you will update this base size is basically after how many samples you are updating the weights. Okay, so say if I am keeping this 1, okay, and again making this epoch 1. Okay, so now see what are the changes in the code. So see, now it is counting up to 40. Why? Because our training samples are 40. So 40 times it is updating the weights of that particular network. Okay, and if I am keeping it to, so see 20 is there. Means after 2 samples, it will update the weights. Okay, and entire database is traced only one time. And say if I am making it here again, say 2 or making it 3. Okay, so it is the first epoch. Same, it is counting for the 20 updates. Then second epoch, it is counting for again 20 updates. And then third epoch, again counting for 20 updates. Is this clear?
Yes, sir. Thank you, sir. Sir, one more thing also, sir. Sir, what if we are adding learning rate? Then what is there happening, sir?
What is, sorry?
When we are adding learning rate, then what is happening there, sir?
Training rate.
Learning rate, sir. Learning rate.
Training rate.
Sir. Learning rate, sir. Learning rate.
I think
Learning rate.
learning rate. Yeah.
Okay. Okay, that learning rate basically we need to define in the part of this optimizer. Okay. So see, I have not written that code in that particular way. So we will go up to here. Learning rate is basically means at what scale you are changing your weights. Okay, so if you are keeping the learning rate, you can say very high. Basically, learning rate is how we are defining the step size that will update the weight in each and every iteration. So if you are keeping the learning rate very small, so your model will converge very slowly, but it will achieve the good accuracy. If you are keeping the learning rate very high, so training will be fast, but your model will not, you can say, get the good accuracy.
Thank you, sir.
And this learning rate exercise you can perform if you can use that SGD, where is it? This optimizer. In this, if you will change that to the SGD optimizer, then you can perform the exercise over the learning rate. Okay, any other question, any other doubt?
Okay, sir. One question in the chat box.
Yes.
Amongst a lot of models, LSTMs, GRUs, transformers, CNNs, how do we decide which is best for our work? That is what properties should we look out for while deciding the most optimal model?
Okay, so see, in the case of deep learning models, actually no one can say with the guarantee that my model is very good. Why? Because all these models are totally data driven. So say you are tuning or designing the model for any specific database. And in most of the cases, this is happening that we are having one database. Say we are discussing the case of this mental workload database. Okay. And we are achieving only say 40% accuracy. So we are looking for some other things. And I say we are doing the artificial synthetic database we are using. So if someone use LSTM in such case, so maybe LSTM perform good without smooth or without synthetic data. So it is just you can say up to the how many database you are using for the validation of your model. So that's why so many type of models are there. But again, all the models are limited to the training data over which they are trained. So we cannot say, or anyone cannot say that my model is best. And even nowadays, one EEG net is very famous to process or to classify the EEG data. But again, if you can change the database, so maybe it will not perform well.
Okay.
Okay, any other questions? Any other doubt?
Sir, I have one more question, sir. One
Yes.
doubt, sir. Sir, actually, if you want to deploy a model in real time, which model we want, which deep learning algorithm we want to use, sir?
Yes.
Sir, in real time EEG analysis, like when the data is continuously coming from the EEG device, we want to detect some certain patterns. So we want to use deep learning algorithm. So which deep learning algorithm should be very fast, and which one should be apt for that, sir?
Okay. So see, for that now, if you are looking for means deployment of deep learning model, and it is, you can say, difficulty. Why? Because so many type of means so many number of parameters are there. Why? Because lots of weight, lots of layers are there. So generally, if you can search for this TinyML. Okay, so again, it is one, you can say, stream, or you can say the branch of the deep learning. It by this TinyML concept, we are able to compress the model weights. Okay, so okay, it is not the part of Para. See, TinyML is basically the concept in which we will compress the model. Okay, so it will be into the memories into the some KBs only. So then we can fit into any specific device. Like you are, have you decided which type of device or microcontroller you are using?
So initially we are using just a PC based, sir. What actually we are doing, we receive the data through LSM using from the emotive device. Then we have a pre-trained model. Then we are matching that that EEG signal with that previously trained model, sir.
Okay, means so some space constraint will be there, huh? Means the memory limitation is there. That's why I think you are asking the question that how we can fit such big a model into a small memory. Is it? Is it the same problem that you are facing?
Sir, actually, when we are using deep learning models in real time, we are faced with the problem is it's slowness, sir. It taking time to give the predictions.
Why? Because the signal need to pass from the so many layers. So that's why it is taking time. So with the help of TinyML concept, even we can reduce the number of you can say layers, and also the quantization levels are you can say suppressed. Means their precision also we are compressing, or we can say losing the precision in the weights. so your model will execute it fast.
Sir, is it a good idea to do like reducing the epoch size and also batch size in real time?
No,
Sir?
no, it is not related to epoch or the best size, because that we need to use in the part of training.
Training. Okay, okay.
So
In test.
once your model get trained, after that you need to deploy that model into the hardware, means on the chip or on some microcontroller.
Okay.
Means you need to perform the training on the computer itself. Once your model get trained and you are happy with the accuracy, then you need to use that model for the real-time application.
Thanks. Thank you, sir. Thank you so much.
Sir, I have one question, a short question. Because
Yes.
the retraining is possible in deep learning and all. So is there anything retraining possible in machine learning? Have you done anything?
Yes, sure. With the help of transfer learning concept, we can again train the already trained, or we can technically say pre-trained model over the new database. Say I am using one mental workload database and I have done the training. Okay. And now I will get some new mental workload database with different classes or with different subject. I can continue the training of same model.
The same thing is for machine learning also. That's what you're saying. It's like a support vector machine or random
For
forest.
that, actually, we have not tried, but yes, we can keep the weight of the last trained model, and we can use from that trained weight itself. That is the concept, and that is the famous with nowadays deep learning techniques, because daily new databases are coming. So simply we are clubbing those learning into the previous learned model.
Okay. Last question, anybody else? Okay, I think there is no last question. I think we can go for that. Vice.
Thank you, Dr. Mithil Kumar Agarwal, for that insightful presentation. To conclude today's impactful session, I now invite Dr. C. Sudalaimani, Scientist C from the Health Technology Group at CDAC Thiruvananthapuram, to deliver the vote of thanks.
Thank you, Vice Chair. It's my great pleasure to present the vote of thanks. I think it's a wonderful talk by Dr. Mithil Agarwal, because it is an very eye-opening technical session, especially for researchers like us who are doing the research work, but having some difficulties in the theoretical part and all, theoretical kind of things. So I think it is very well covered, and it's very nice. We cannot we cannot forget the knowledge what we have gained from this. I think it has provided a lot of insights to our practical problems, and our work also we can include all these knowledges. Thank you, sir. And I expect the similar kind of sessions we may further provide. Thank you, sir. Thank you.
Thank you very much, sir. And I also means very thankful that Mani sir started this particular series, because since from the last 10 or 15 year I am working in this EEG and BCI domain, but no one is taking the initiative to you can say start the series of this BCI. And even in means not this particular title or subject is not in the mainstream, but in foreign countries lots of research is going in this particular area. So it is very means a good initiative taken by the Mani sir. So
yes, sir.
thank
Yes,
you and
actually,
congratulations, sir.
Yeah. We initiated these thought things, because even though BCA is the future technology, but in the government sector or wherever, the initiatives for providing more research funding is very less because of the complication of the problem. So we want to take up this up to government level and also bring a network of people who are working in this area. So we can collectively tell that what is the real world requirement, how we can collectively work together for creating a useful and easily wearable BCI devices as well as BCI algorithm. That is our motive. Of course, the BCI kind of thing we can extend to disease detection, that is neuroscience also. So that is our main motto, sir. Thank you for your support. I think we come to you for further sessions, sir. We can continue this as a series.
Sure, sir. Sure.
Okay.
Thank you. Thank you, Manish, sir. Thank you,
Yeah.
Vaishnavi, and all the participants who attended this lecture. Thank you. Thank you very much.
Thank you. Nice.
With that, we come to the end of this enriching session of the ICON BCI lecture series, part 5. Thank you all for your valuable presence and active participation. Wish you a wonderful evening ahead. Thank you.
Thank you, sir. Bye. Bye
Thank
to
you.
all.
Bye, sir. Thank you. Thank you.